Alright, Math 3, let's take a look in our workbooks. 4B.4.1. You should have already tried out this warm-up on page 103 so that you can just kind of follow along. Then we'll take a look at some notes and go from there. So we've got three functions here. We've got an exponential, a quadratic, and a linear. Okay? So they use it to describe the increase in a prairie dog population. In each function, x is number of years, and the y is the population in hundreds. So let's answer some questions. So it says determine the average rate of change over the domain interval of 0 to 1. So that's basically, we're looking at where the graphs are right here to where they are up here. Okay, and if we notice, the linear and the quadratic are basically the same. The exponential starts up a little higher, so that'd be 1, 2, 3, 4 up, and to the right 1. So it would have a rate of change of 4 over 1, or just 4. Okay, whereas the other two, they just go 1 up more, so it'd be 5 over 1. Okay, for the other two, or just 5. So that means every year they have either 400 more or 500 more. Okay. Now it says compare the y-intercepts of the function. So once again, these guys start with 0. Okay, so that means when you'd measure the population, there weren't any in those two models, the linear and the quadratic. In the exponential, you would have so that was linear and quadratic. For exponential, you'd have 1, so that means they started out with 100. Okay, that's what it means in the context. It says, what is the solution for the system of all three functions, and what is the meaning in the context of the problem? So the solution, remember, is where they all intersect. So they all intersect right here at 1, 5. Okay, and what does that mean? It means after 1 year, we have 500 prairie dogs. Okay, there's the warm-up. Alright, so now let's take a look at some examples. So we're going to be looking at some functions, some linear, quadratic, exponential, and kind of figuring things out with them. Okay? Alright, so example 1 says a function commonly used to represent bounded growth of a real-world function value is the exponential / linear combination function of the general form f of x equals a times 1 minus b to the negative x, in which a represents a horizontal asymptote, y equals a, toward which the values converge. Use the following graph to determine a and b using this point, 1 and 8/3, then write an exponential linear combination function that models the graph. Okay. Alright, so we need to figure out what a and b is. Okay. Well, the first thing, if I look at this, okay, maybe if we see right about there, it looks like it's got a horizontal asymptote at y equals 4. So a should equal 4. Okay. Now, in order to find b, we've got a point that we're going through, so we can use this point to help us figure it out. Okay. So that would give us an x and a y, or an x and an f of x. So I'd go 8/3 equals 4 times 1 minus b to the negative 1. Okay? So we'd have 8/3 equals 4 times 1 minus, remember, a negative exponent makes it a fraction. So then we can probably distribute the 4. So we get 8/3 equals 4 minus 4 times 1 over b would be 4 over b. Okay? Then what I would do is I'd times everything by b, because I don't like b's being on the bottom. So I'd get 8b over 3 equals 4b minus 4. Okay? Then we'd subtract the 4b. So I'd have 8/3 b minus 4b. Okay, well 4, isn't that the same as 12 over 3? Okay, which, if that's the case, 8 minus 12 would give us a negative 4/3 b would equal negative 4. we could times by the reciprocal, so a negative 3/4, times by negative 3/4 on both sides. 3's cancel, 4's cancel, it's negative. We get b equals, negatives cancel, 4 over 4 leaves us with 3. So b equals 3. So for our equation, we would then go f of x equals 4 times 1 minus 3 to the negative x, and that would model that graph. Okay? And that's pretty complex, but that's all we need to do. Alright, example 2. The graph models a distance, s of t, traveled by a speeding car moving at a constant rate of 80 miles per hour, and the distance covered by a state patrol car, p of t, until the patrol car intercepts the speeding car after 5 seconds. The general equation for the cars are s of t equals r times t for the speeding car, and p of t equals 1/2 times a times t squared for the state patrol car, in which a is the acceleration in miles per second squared. Write the specific equations for the two distances at a time of 5 seconds and determine appropriate horizontal and vertical axis scales on the graph to reflect the given problem conditions. Okay, well then. So first of all, we've got to connect them to the same timeline, okay? Because the car is 80 miles per hour, all right? So that's its rate. So if we'd go s of t equals 80, then times the time. Okay, but that's in hours, 80 miles per hour. So we need to figure out how many miles per second we would get. So to do that, we want to think about, 80. We have 60 seconds, right, in a minute. We have 60 minutes in 1 hour. Okay, so if we simplify these, okay, we go 60 times 60, because 1 times 1 is 1, and we get 3,600 seconds would give us an hour. Okay, so now we know with our 80 miles per hour, okay, we're going that miles per hour, so we go 80 miles per 1 hour, okay, and we times that by this fraction, because we could flip it. 1 hour equals 3,600 seconds, so the hours would cancel, and we'd have 80 over 3,600, which we'd simplify to, oops, wrong way, I times instead of dividing, which would give us basically, for every mile, because miles on top, it'd be 1 over 45, so for every mile, it took us 45 seconds, okay? So 1/45 of a mile per second. So our rate in seconds is really 1 over 45, okay? Now, if we look at our equation, we wanted it after 5 seconds, so we times that by 5. So if we went s of 5, I guess technically this is t. So if we went s of 5, that would be 1 over 45 times 5, okay? Which if we multiply that, that would be 5 times 9, 5s would cancel. So s of 5 would equal 1 over 9, okay? So if we're looking at this point after 5 seconds, okay, this time of 5 seconds would give us a distance of 1/9 of a mile, okay? Now, since that's the point where they're the same, to help us figure out this patrol car, okay, we know the t value is 5 right here, and the p of t would be 1/9, same as s of t. So I can go like this. We can go p of t is 1 over 9 equals 1/2 times a times the time, which we know is 5, times 5 squared. Okay, then we can solve for a. So we would end up with 12.5 squared, which is 25. 1/2 times 25 would give us 12.5a equals 1/9. Okay? So we would then just divide by 12.5. So I'd go 1/9 divided by 12.5. And that would give me a very small decimal. So maybe we want to figure this out with fractions, since we've been doing everything else with fractions. So if we went 25/2 times a, then we could cross multiply. We'd go 9 times 25, which would be 225a, equals 1 times 2 is 2. Then we divide by 225. So we'd get 2/225 would equal a. Okay? So the acceleration would be 2/225 miles per second squared. Okay? So our equations would end up looking like this. So s of t would equal 1/45 times t, and p of t would equal, well, this would be a, but we had 1/2 times a, so 1/2 times 2/225, the 2's would cancel, so 1/225 times t squared. Okay, so those are our equations, and that was a lot of work to just find those two measly equations, wasn't it? Now we've got to figure out the scales, okay, how we want to deal with that. Alright, well, if we look at this, we know that this is equal to 1/9, this distance, but there's 10 boxes. Okay, so essentially we'd go 1/9 and divide that by 10, and so each of those, the boxes, would represent 1/90th of a distance. Okay, for our scale right there. Alright, now if we look at these scales, for each box there's 5 seconds, and each one of these tick marks, that gets us up to 50, and it was 5 seconds total, so each big box could just be worth 1 second, so each little one would be worth 1/5 of a second. Okay? Not too concerned with the whole scale issue. Anyway, let's jump to example 3. So it said cloud storage refers to keeping data on a remote database instead of your own computer or mobile device in order to save hard drive space. Cloud storage users pay for this service either as part of a data plan subscription or separately. Two market research teams use function models to describe the declining cost of cloud-based computer storage services. Team A used an exponential function represented by A of t. Team B used quadratic by B of t. The graphs of the functions are shown over a 10-month period, with the present represented by the region at which both models reach a maximum function value. The y-axis represents the price in dollars per gigabyte of storage. Domain values that are greater than those represented by the minimum points are projections based on the models. Describe how well the two models fit the data of changing cost of cloud storage. Use function characteristics to compare the models. Describe the limitations of these models for predicting future changes in the cost of cloud services. All right. Well, I think first of all, if we look at the quadratic function would mean that prices are going to keep going up. Once they go down and hit this minimum point, they will then start to go up. Okay? So, I think the exponential would be a better one for fitting the data, because most likely it's just going to get cheaper and cheaper to store data, therefore cheaper and cheaper to do that. So I think that one would fit better. Now, something could happen that comes along that's better, and then possibly it would go up because less people would be using it, so they'd have to charge more. But I don't really see that happening in a way that, you know, if something better comes along, it's probably just going to kill it. So yeah. All right, now let's find the equation for both of these, because I think that's really what we wanted to focus on here. So, looking at the quadratic, we can find its vertex, which would be 6, negative 2. And if you recall, there's the vertex model formula, b of t, and that's a times x minus h squared plus k. So, using that, we can figure out what our equation would be, okay? Knowing that we have these two pieces of information, that's our h and our k. So we'd go b of t would equal a times x minus 6 squared minus 2, because plus k would be plus negative 2, which is negative, just minus 2. Now, to figure out this a, we can pick a point on this graph, which I would pick an easy one like an x-intercept, 4, 0. That would give us an x and a y value, so I can go, this would be like the y value, so I'd go 0 equals a times the x value of 4 minus 6 squared minus 2. And then we can simplify. I'd add 2 to both sides, so 2 would equal a times 4 minus 6 would be negative 2. Negative 2 squared would be 4. 4 times a would equal 2. Divide by 4, and we'd get 1/2 for a. So my equation for b of t would be 1/2 times x minus 6 squared plus 2. And that would be my, or not plus 2, minus 2. There we go, minus 2. And that would be my first equation. Okay. Now, to find the exponential, we have a problem because we can't really see where the y-intercept is. Okay. We should notice it's a decay one, so it's going to have issues with its exponent. Now, a form that we can use for that one would be this format. A plus e, remember that number e, natural log of b minus x. Okay? Now the a is going to be our horizontal asymptote, which it looks like pretty easy to see. It's down here at negative 2. Okay? Now, before we move on, I just spotted a mistake. That should actually be a variable of t, so should that one, since it's b of t and a of t. So now, in order to figure out what e is going to be, because that will be a number, we need to use a point here. Okay? So if I look along my graph, I can see a point here for the exponential at 4, negative 1. So it would be negative 1, let's do that over here. Negative 1 would equal negative 2 plus e to the b minus t, so b minus 4. Or just minus 4, huh? Okay. So then we'd add 2 to both sides. So we get 1 equals e to the b minus 4. Then remember, back to logs, we could change this to the natural log, right, of 1 would equal b minus 4. Now if we type natural log of 1 in there, we get 0. So then we just add 4. So b would have to equal 4. So our equation for a of t would be a of t equals negative 2 plus e to the 4 minus t. Kind of a crazy looking function. Okay? So, like I said, I think that's probably enough for that problem. We will call that one good. Okay? Let's take a look at this problem-based test now. So, I want you guys to try this one on your own. So, take a look at this. I'll explain a few things with it, then have the substitute pause the video for a bit so we can take you guys can try it on your own, and then you can start it up and see where you're at. So, an internet market research company compared the growth in users of a popular social media website in the United States with the site's user-based growth in the rest of the world. The graph and the table show the number of active site users in the millions for each quarter of a year from 2010 through the third quarter of 2013. The market researchers want to compare and project the growth in the two markets using exponential, linear, and quadratic function models. Use the table data and a graphing calculator to generate exponential, linear, and quadratic function models for the United States users and non-United States users. Then graph the models and see how they compare to the data points shown on the graph, which function models would be best for each set of data points. Alright, well, I'm looking at this and just realized that you guys probably don't have calculators in your room. So we will have to take a look at this one when we get back. I think it's a good one to look at. But being that we're not even in our same room, and you may have forgotten how to figure some of this stuff out, we are going to have to deal with it next time. Okay, and I'll show you how we can do that, and we'll go with it from there. So for now, let's take a look at our homework, pages 111 to 112, 4B.4.1. So I want you guys to get to work on that. Okay?